Hey guys, in today's video we would be looking at the interface thermal conductivity equation, and we would be deriving the equation for the interface thermal conductivity, and we would be comparing it with our general equation what we've already discussed in the previous video. So before going into this video, I'll just give a quick recap about the process involved in FVM. The first step is discretization, wherein we divide one fixed volume into multiple control volumes, and the second step involves integration over that control volumes over the centroid, and in the third step we use interpolation techniques to give out a generalized form, right? So this is the process of discretization, where you're dividing one control volume into multiple control volumes. And now in the second step we'll choose one particular control volume and integrate, and in the third step we would be interpolating. Now when I talk about interface thermal conductivity, we know that the 1D steady state heat conduction equation is this. Now as I discussed in the earlier video, we have source terms involved for heat transfer and turbulent kinetic energy equations. So we also have a source term, and this would be the final equation. Now let us say heat transfer is happening across this slab. The first step involves discretization. We take this slab and we discretize it into different control volumes. Let's say this box, what I'm showing, is one control volume. This is the neighboring box, which is another control volume, and this is another box which is showing another control volume. Now P would be the centroid for this control volume, E and W would be the centroids or the grid points for the respective control volumes. Now when I talk about small w and small e, these are the faces. I'll just show it to you. So small w and small e represent the faces, okay, and capital W and capital E represent the grid points. Now I'm done with discretizing, right? And the second step, I got to integrate this. I take the same equation here and I just apply the integral over it. When I apply the integral over it, I'm left with these terms, and since we are dealing with this particular control volume, our limits would be E to W, so that's what we apply in here. So integral of d of k dt by dx would result in this. Since I'm applying limits, it would be k dt by dx at E minus k dt by dx at W, plus the integration of the source term. Now I can approximate the integration of the source term as dx as s bar times delta x, where s bar is some average value over the control volume. It would approximately be the same as this. So we assume the approximation function here. Now before going and giving out a general equation, we need to know k dt by dx at E and k dt by dx at W. And in order to know that, we assume a few more things. Let's say this is the temperature and this is the thickness. This is the grid point W, this is the grid point P, and this is the grid point E. W and E are the faces respectively. Now we assume that the temperature increases linearly, okay, with the distance. That is, at W, P and E, they have linear relationship, that is temperature varies in a straight line. And also these constant lines, what you see at each of the grid points, says that the temperature at this particular control volume will only prevail in this control volume. So it's constant throughout this control volume. And again, it increases at this point and at this point, right? So this is the assumption what we make. Now, so we can write k dt by dx at E would be nothing but the slope, right? Because this represents the slope. We have k at E minus the slope would be the change in temperature by thickness, that is Te minus Tp by delta Xe. It's the same thickness what is shown in here, delta Xe, between P and E, and delta Xw stands between W and P. So we get this equation here, and the same for k dt by dx at W. The slope would be this, Now when I substitute these two equations in equation number 1, I would be left with KTE minus TP by delta XE minus KW TP minus TW by delta XW plus, as I already told you, we would be considering the integration of the source function as S bar times X, where S bar is an average value of the source term and the fixed control volume. When I condense this equation, we would be getting this equation. That is, I just rearrange the terms on both sides, take TP in common, and I'm left with this. Now we can write this in standard form or the general equation by considering KE by delta XE plus KW by delta XW as AP, KE by delta XE as AE, KW by delta XW as AW, and this as B. Right now, and this would be our general form. For 2D and 3D, what we can do is we can just apply a summation function here, okay, where we can write AB times TP is equal to ANB plus TNB, where NB is the neighborhood points. For example, in here we had two neighbors E and W. For P we had two neighbors E and W, so we're getting it as two different points, and that's how the summation works.